Hello, it's Dumplet here. Here's an item on algebra. A, B, C, and D are real numbers in the question, and we're given that m plus the square root of n times the imaginary constant I is a common root to two cubic equations, x cubed plus ax plus b and x cubed plus cx squared plus d equals 0. And we're also given that negative 20 is a root to x cubed plus ax plus b, and negative 21 is a root to x cubed plus cx squared plus d. Now we're given that m plus square root of n times I is a common root. Find the value of m plus n. So m and n are positive integers in this case. Credits to the American Invitational Math Examination for this item. As usual, pause this video if you'd like to give this item a try. But if you're done, let us dive into the solution. Now, the first thing that we know is that, there is an imaginary root to these two equations. And combining with the fact that we do have the negative 20 to be a root to the first one, negative 21 to be a root to the second one, let's make use of the factor theorem for now. So we do have x cubed plus ax plus b and x cubed plus cx plus d. We know the roots of those two. And by the factor theorem, I know that, x plus 20 is a factor to the first one because negative 20 is a root. And then I know x plus 21 is a factor to the second one. Now, the remaining factor, which must both be quadratic, because we do have a cubic and we were able to factor a linear factor out, those two terms here, they must be quadratic. Now, let's try to use the rule of the quadratic surds, because we do know that m plus the square root of n times I, it is a root to these two equations. And in fact, it should be a root to the quadratic here. And by the rule of quadratic surds, it is known that, since m plus the square root of n times I is a root, then the m minus the square root of n times I should also be a root. And so it must satisfy that these two roots are the roots to obviously whatever is the quadratic equations here. In fact, this is going to give us the conclusion that, these two factors must be exactly the same. So that's going to be the thing. Now, let's try to use some principles to allow us to kind of roughly get what that is. We know they must be quadratic and it's going to be monic as well. So the leading coefficient must be 1. But we could do better here because, we do know that first. In the first equation, x cubed plus ax plus b, there is no x squared term. So by Vieta's formulas, the sum of the roots of this polynomial is going to be 0. So we do know that we do know that negative 20 is a root to this equation. So we know that in the quadratic here, the sum of the roots here must be 20. So the sum of the roots is 20, so that's the best thing we could have. So we know that x squared plus 20x, minus 20x, because we want the sum of the roots to be 20. Let me just generally write this as p for now. I have no idea what the roots are, but we know that it must be of that format. I could do something similar to the second one. Now, in the second equation here, we do observe that there is no x term. And that tells me that the sum, when taken 2 at a time, that's going to be 0. So the sum of the roots taken 2 at a time, it's going to be 0. Now, we do know that negative 21 is a root. And let's just say we consider negative 21, and let's just say the other two roots are r and s. So taking the sum of the roots when taken 2 at a time, it's going to be negative 21r. So we know this must be 0, negative 21r plus negative 21s. So essentially a negative 21s here, plus rs, that should be equal to 0. And in fact, I could get the nice relationship here that 21 times r plus s, that's going to be equal to rs. And I don't know what the roots are or what the sum and the product is, but I could try to let stuff for now. Let's just say the r plus s over here, let's just make this q. If I make that to be q, then I know the quadratic here must be x squared minus qx. So I let the sum of the roots to be q. And the product of the roots is essentially going to be 21q, right? And that's going to be the way we could write this quadratic equation. Again, that's not considering that we know already that these two are the same. Now we're going to consider that they both must be the same. So we do have these two, x squared minus 20x plus p, and x squared minus qx plus 21q. And based on the rule of the quadratic surds, as presented earlier, we know that these two must be exactly the same, right? So we could just do some comparing of coefficients. We know that the negative 20x should equal to the negative qx. So negative 20 should equal to negative q. That's obviously going to tell us that q equals 20. And then p and the 21q must be the same. P must be equal to 21q. And since q equals 20, p equals 21 times 20. And that's going to be equal to 420. And that's going to get us the values of p and q. So we would know that this factor, I'm just going to take the top one, it's going to be x squared minus 20x plus 420. And we did note that a while ago, it must this root must satisfy the quadratic equation. And I know that there's going to be two roots, but then again, because of the rule of quadratic surds, both is going to satisfy, but we're just going to focus on the positive root here, or the root with the plus sign in the middle. Now, I think it's easy to solve this quadratic equation. Any method will do here, but I'm just going to use the completing the squares method. So I know that x squared minus 20x plus 100 is a perfect square. I'll just do this additional 320 here. And I'm going to move the 320 to the other side. So this would be an equals negative 320. And this is a perfect square. And I'm ready to take the square root of both sides. So x minus 10, it's going to be equal to plus or minus the square root of negative 320. So this is going to be the square root of 320 times the imaginary constant of I. And I would be able to get here that x is going to be 10 plus minus square root of 320 times I. And that's the reason why I didn't simplify, because we already have this nice format anyways. Again, we're just going to take the positive root, but no worries, because it's not really going to matter anyways. But we would know that the root that we're finding is going to be 10 plus the square root of 320 times the imaginary constant I. So m plus n, which is going to be 10 plus 320, that's going to give us the final answer of 330. And this will be our final answer. Hopefully you guys learned something new from this video, and I'll see you in the next one. Bye bye.